Hello guys, this is Edward from EdSTEM. Today I'm going to be explaining how to interpret mass spectra of organic molecules. By the end of the video, you should be able to identify the fragments forming peaks in spectra of organic molecules. We understand that in mass spectrometer, the atoms get ionized when a fast-moving electron is bombarded with it, right? So that makes the atoms become positively charged. This positively charged ions then travels down to the detector where they are detected, and the mass of the ion is then recorded as the M to Z ratio, that is the mass to the charge ratio. Okay, now in terms of isotopes, so if the atoms has more than one isotope, so we are going to have like more than one peak, right? So let's say you have 1 and 2. So this is basically how mass spectra of single atoms and isotope look like. But in case of, in terms of organic compounds, they're quite different. It's literally impossible to see an organic spectra, a spectra of organic compound that has just one peak. And the reason is because organic molecules consist of chains of carbon atoms linked together. Okay, so now we're going to see how the spectra of organic molecule look like. Okay, now pentane is C5H12. Right, so we have CH3, CH2, 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 and CH3. Okay, so usually the last peak is called the molecular ion peak. That is the molecular mass of that particular compound. All right, and on this axis we have the relative abundance. Okay, or some cases you might see relative intensity. Okay, it might be written as relative intensity. They are basically the same thing. And here on this axis we have the mass to Z ratio, that is mass to charge ratio. So the tallest peak you can see here is called the base peak. It's called the base peak. All right, that is the most abundance of the fragments. Okay, the most abundant fragments. All right, so now let's look at the fragmentation of pentane. First of all, this is what I'll do. I will number my carbon atom 1, 2, 3, 4, and 5. Now, when carbon atom number 1, when bond between carbon 1 and 2 are broken, are fragmented, right? So it's possible you're going to have a methyl. Here is a methyl cation. You're going to have a methyl cation, and this is a butyl and a butyl radical. Here is methyl, right? Now, also we can also have a methyl radical and a butyl cation. So practically it means when the bond between carbon 1 and 2 is broken, you can have a methyl CH3 plus, and also you have a butyl C4H9 plus. Okay, now what if carbon 2 and 3, bond between carbon 2 and 3 are broken? So we are going to have, it means we're going to have ethyl, and also we're going to have a propyl cation. Okay, so if you have bond 2 and 3 broken, we are going to have an ethyl cation C2H5 and propyl cation C3H7. Okay, so basically bond 3 and 4 is the same. Breaking bond 3 and 4 is the same as breaking bond 2 and 3, right? And breaking bond 4 and 5 is the same as breaking bond 1 and 2. So in this um, compound, if it's fragmented, we're going to have these fragments. We're going to have peaks. You're going to have all these peaks represented in the spectrum. Okay, so now let's identify which of the peaks correspond to these fragments. Okay, so let's start with this with propyl. This is propyl, right? Now what is the mass of propyl? C3H7, 12 times 3 plus 7. Okay, and that is 43. So this corresponds to the peak here at 43. That is the propyl. Okay, so you have C3H7 plus. Okay, so let's look at this, the ethyl cation. Okay, and that is C2H5. If you add them together, 12 times 2 plus 5, we have 29, and that corresponds to this peak here at 29. So this is our ethyl cation fragment, C2H5 positive. Okay, and let's look at this C4H9. That is our butyl carbocation, right? That will give us 12 times 4 plus 9, 57, and that corresponds to this peak here. So C4H9. I hope that makes sense now. So that's how to identify fragments that belongs to peaks in mass spectra. Okay, now if you look at this mass spectra, this you have a base peak at 43, and that corresponds to peak of propyl, right? Propyl cation, right? Why is it the most abundant? Why is the most abundant? Why not a butyl carbocation, or why not ethyl carbocation? Why is propyl carbocation the most abundant? If you can just pause the video and have a think about that, just give it a thought and see what you can come up with. Now the reason is this. Remember, in terms of stability, okay, a secondary carbocation is more stable than a tertiary carbocation rather is more stable than a secondary carbocation, which is more stable than a primary carbocation, and a primary carbocation is more stable than a methyl cation. Okay, so methyl cation basically is the least stable, right? Now let's look at the scenario when you break bond between carbon 1 and 2, we have a methyl cation, right? We have a methyl cation produced, and a primary butyl carbocation, right? But if this methyl cation is less stable, right? So it will be difficult to break this bond between 1 and 2, all right, because of the presence of methyl carbocation that we produce. Now compare that to when carbon 2 and when bond between carbon 2 and 3 are broken. So if you break a bond between carbon 2 and 3, we have a primary ethyl carbocation and a primary propyl carbocation. All right. Now these two carbocations are more stable than methyl cations, so it will be easier for this bond between 2 and 3 to be broken. Hence, we have a more abundant propyl carbocation, which is the base peak at 43. I hope that makes sense. Okay, so this is the mass spectrum of one propanol. As you can see here, it's quite different from the simplified spectrum of pentane. However, there is nothing to be worried about. It's basically the same thing, just that we have little peaks. Okay, now all these smaller peaks are mostly as a result of isotopes. Okay, they are as a result of isotopes. So what you need to do is first of all identify the each clusters, right? We have this cluster here, we have a cluster here, we have a cluster here, we have a cluster here. Then on each cluster, identify the highest peak, okay, from each cluster. Now we know that the peak at the last peak are usually the mass, the molecular mass of the compound, okay, the M plus, all right, and one propanol has a molecular mass of 60, right? So this 60 here is our M plus, that's the molecular mass of propanol. Now you'll be wondering, what about this peak at 59, which happens to be the tallest here. Now 59 is as a result of isotope of carbon. Okay, now if we have carbon 11, because of carbon 11 we have this isotope here, we have this peak here at 59. Sometimes you might see a spectrum that will have a peak after the M plus. That is also as a result of carbon, the isotope of carbon 13. All right, so there is nothing to be worried about, right? So now we have identified this particular cluster, right? Now so let's draw the structure of one propanol. Okay, now so propanol is HCH3, right? Then CH2, then we have hydrogen, OH, and H. Okay, so now we've identified this, the mass of this compound, this structure here, to be 60 here. Now let's number our carbon 1, 2, 3. When carbon bond between carbon 1 and 2 is broken, okay, so we're going to have a methyl. You're going to have this is a methyl, right? And methyl is 15, right? So and this 15 corresponds to this cluster here, this peak here. This is 15. This is our methyl cation. So we have CH3 plus. Okay, so so let's put in this one. This one is the molecular M plus, which is basically this whole structure here, right? Now then this one here, the remaining one will be, if you subtract 60 minus 15, that will give us the value for this, right? So that give us 60 minus 15. Now we have 45. Do we have peak at 45? We have 41, 42, 43, 44, 45. Now we have 45, but it's almost not existing, right? But it's there. It's very small, very little. Okay, difficult to see. Now that is because it's less abundant. That's because it's less stable. Now note that during fragmentation, it's possible for hydrogen to lose hydrogen during the process. Okay, so when that happens, you're going to have, for example, in this case now, in this cluster here, we have the highest peak at 42, right? This is 40, 41, 42, and all this is 45. This is 45, right? So it means that during the fragmentation, we have 3 hydrogens were lost during the fragmentation. All right, so this 45 here, sorry, 42 rather here, correspond to this cation fragment, which is C2 CH and OH cation. So that is what corresponds to this peak at 42. I hope that makes sense. All right. Now, what if we break bond between carbon 2 and 3? So we are going to have this. We are going to have all this. Okay, and an ethyl carbocation, right? We're going to have an ethyl, which is C2H5, all this, and then we're going to have this CH2, this is a carbocation, then CH2OH carbocation. All right, so let's look for the value of this carbocation here. CH2OH, that is 12 plus 2, 12 plus 2 plus 16 plus 1, that is 31. 31. So that corresponds to this base peak at 31. Okay, so that is our C. So you can just put the structure here. OH cation. Okay, then our ethyl C2H5 carbocation, that is ethyl carbocation, 12 times 2 plus 5, 29, and that corresponds to this peak at 29 here. You can see this peak at 29. That is our ethyl carbocation, C2H5 ion. Okay, so this is a mass spectra of methyl ethanoate. Methyl ethanoate. Okay, so identify the fragments that correspond to the peaks here. Pause the video and give it a try. Okay, so let's do that together. So I told you first thing to do is to identify the clusters, right? We have this cluster here, we have a cluster here, and here we have a cluster, we have a cluster here and here as well. Okay, so and the last fragment, the last peak is usually the M plus, like we should know by now. That is the molar mass of the methyl ethanoate. Right, so let us draw the molecular structure of the methyl ethanoate. Let's draw the structure of methyl ethanoate. So this is methyl ethanoate. Let's look at the fragment and identify the one that corresponds to the peaks here. Okay, so first what we do is to number the carbon atoms. We have 1, 2, and 3. Okay, so if the bond between C1 first carbon atom number 1 and number 2 are broken, okay, so we're going to have a methyl carbocation CH3, right? And CH3 is 15, right? And that corresponds to this peak at 15 here. So this 15 here is CH3 plus. Then it means we can also have this as our cation as well. Okay, and this will be equal to the molecular ion minus 15. So molecular ion of methyl ethanoate is correspond to this peak here. Okay, that is our M plus, which is 74. So 74 minus 15, that will give us 59, and that corresponds to the peak at 59 here. So at 59 we have this fragment. We have this fragment at 59. Then CH3. Okay, this is the fragment at 59. Okay, now what if you break bond between if you break this bond here between C2 and oxygen? Okay, if you break these bonds, we're going to have this and also this cation and also this cation from here. All right, so let us find the value of the two cations there. So let us find the value of the two fragments there. Now, these fragments will give us, this particular fragment here will give us 43, and that corresponds to the base peak at 43 here. This is 43, right? So these fragments correspond to the base peak, and that is this H, C, H. Okay, oxygen. These fragments correspond to 43. And let's look at this other fragment, the value of this other fragment here from this side. So basically 974 minus 43. And that gives us 31. And that 31 corresponds to this peak here. This shows that, now this 43 shows that it is more stable. Okay, it shows that this particular fragment is the most stable fragment produced, right? And the other fragment at 31 is the least fragment produced, and that belongs to this particular fragment. So it's unstable. One is as a result of loss of hydrogen from this fragment here. Loss of how many hydrogen? 2 hydrogens. So if 2 hydrogens are lost from this fragment here, we have the peak at 29 rather. Okay, so this 29 is as a result of this fragment CHO plus. Okay, I hope that makes sense. I hope we have been able to identify the fragments that correspond to the peaks in this spectrum of methyl ethanoate. So that will be the end of today's video. Subsequently, I will be making videos on how to interpret mass spectra. Now, this is quite different from identifying the fragments, which is what we did right now, right? But the one I'm going to do later on is going to be for postgraduate levels or perhaps undergraduate level, because you will be given a spectra and you'll be told to identify the spectra without any information. Okay, so I'm going to make a video. I'm going to explain how to do that, and if you want to do that as well, if you want to be part, you can you feel free to watch the video. Okay, and if you haven't done so, kindly subscribe to my channel, like the video, drop a comment if you have any question, and do not forget to turn on your notification bell so you get notified whenever a new video like this is dropped. See you some other time.